Hi everybody, in this video I want to talk about the postulates of special relativity. The postulates themselves are relatively simple, but the implications, which we'll explore in future videos, are bizarre and profound. So in order to better understand those bizarre implications, we want to first make sure we understand the postulates. Alright, so the first postulate of special relativity is that the laws of physics are the same in all inertial reference frames. This postulate actually dates all the way back to Galileo, and to talk about this postulate, to illustrate, I'll use an example that dates back to Galileo. All right, but first, what does this mean? Well, first, a reference frame. A reference frame is just a set of coordinate systems that are fixed relative to each other. So first, let's imagine nailing a coordinate system to me. Attach this here, attach this there. So I've got an x-axis, a y-axis, I've nailed it to me. If I move around, the coordinate system moves around with me. So the coordinate system is part of my reference frame. We can add another one. Let's add a coordinate system right here, y-axis and x-axis. That's also attached to me. This coordinate system and this coordinate system, they both move along with me. They both move along with me in exactly the same way. They're fixed relative to each other. They're nailed to me. This coordinate system, and me, we're all part of the same reference frame. We could call that my reference frame, a reference frame attached to me. Okay. Inertial, in this context, in the context of special relativity and in the context of Newtonian physics, typically means not accelerating. There are other contexts in which inertial may take on different, more extended meanings. We're not going to explore those here. Inertial, meaning not accelerating, is good enough for us and is good enough for special relativity in this context. Okay, so let's imagine we have an inertial reference frame represented by this coordinate system and all other coordinate systems that are at rest relative to this coordinate system. Now let's imagine another coordinate system, another reference frame, moving at constant velocity relative to the first one. Well, if this one is moving at constant velocity relative to this one, that means it's not accelerating relative to this one. So if this one's inertial and this one's moving at constant velocity relative to the first one, it will also be inertial because it's not accelerating relative to the first one. So once you establish one inertial reference frame, all other reference frames that are not accelerating relative to that first inertial reference frame are also inertial. All right. So that's just some background. All right, so here's an example. And this example dates back to Galileo. Let's imagine this example where I hold a ball up here, and then I have my other hand right below it, and I drop the ball. Now, let's analyze that example with an idea toward thinking about reference frames and so forth, and what it means for the laws of physics to be the same in inertial reference frames. All right, so to analyze this motion, we'll crack out Newton's laws. So we'll draw a free body diagram of the ball from the time it leaves my hand to the time it hits my other hand. So while the ball is in free fall, we draw a free body diagram of the forces acting on the ball. There's our free body diagram. We have the downward gravitational force. There's no other forces acting on the ball, so the acceleration will be downward. And since the ball had no initial horizontal velocity, it won't pick up any horizontal velocity because there's no horizontal acceleration. Acceleration's got to be down. So therefore, the ball ends up falling straight down, and it falls faster and faster as it goes toward my hand. Great. All right, so now let's add a wrinkle to this. Instead of me just standing here, let me move at constant velocity relative to the board. Great. Now, there's a couple different ways I can analyze this. I can analyze this from the frame in the context of a reference frame attached to me, or I can analyze it in the context of a reference frame attached to the board, or attached to something else. First, let's analyze it in a reference frame attached to me. So here's my x-axis, here's my y-axis. Those move with me. So now I'll drop the ball. Well, In my reference frame, the analysis hasn't changed. In my reference frame, the ball's at rest. Yes, I'm moving relative to the board, but the ball's moving along with me relative to the board. The ball is not moving relative to this coordinate system that's attached to me. Remember, I have a coordinate system that goes y, x. As I move this way, the x and y coordinates of that ball are not changing in a coordinate system attached to me, right? So if this is the origin, the x coordinate of the ball has not changed as I move. So in my reference frame, the reference frame attached to me, the analysis is the same, whether I'm just standing here or whether I'm moving at constant velocity relative to the board. The analysis from my frame of reference is the same. But now let's look at the analysis from the frame of reference of the board when I'm moving to the right relative to the board. Relative to the board, as I move to the right, I'm carrying the ball along with me. So the ball has initial rightward velocity when I let it go. So in this frame of reference, the ball has an initial rightward velocity. I should stop and draw free body diagram. In this other frame of reference, well, as soon as I let go of the ball, the only force acting on the ball is a downward force of gravity. So this is still the free body diagram. So we still have a downward gravitational force, no other forces. The net force is downward, so the acceleration is downward. All right, so the ball will accelerate downward in this new frame of reference. But as I mentioned before, since I'm moving to the right relative to the board in this frame of reference, I'm carrying the ball along with me. The ball had an initial rightward velocity. There's no rightward acceleration, but it had a rightward velocity, and so the ball continues to move to the right along with me. So as I move to the right, the ball moves to the right, so that by the time the ball has fallen to hit my hand, it hits this hand just below my other hand. All right, so Newton's laws allow us to analyze the motion of this ball in both frames of reference, a frame of reference attached to me or a frame of reference attached to the board, and me moving relative to the board. Works just fine. I want to note, of course, this picture is a little bit exaggerated. In the time that the ball dropped, I didn't actually move that far. I just exaggerated this to make it more visible. This would be what the picture would look like if I was moving really fast to the right relative to the board. All right. So the laws of physics being the same in all inertial reference frames, in some ways that's not a big deal. We've been assuming that since Galileo. That's basically one of the things that allows us to do physics at all. Where things really start to get strange is with the second postulate of special relativity, which says that the speed of light in vacuum is the same for all observers, regardless of relative motion of the source or the observer of the light. And that universal light speed, by the way, we give the symbol lowercase c, which is about 3 times 10 to the 8th meters per second, or 300 million meters per second. All right, so this postulate is highly counterintuitive. And to see that, let's just set aside light for a moment and think about people and baseballs and cars. Imagine a person has thrown a baseball. And let's imagine at the arc of its trajectory, at the top of its trajectory, the baseball is traveling to the right with a speed of 80 miles per hour relative to the person. Imagine, meanwhile, that a car is zooming past the person, heading to the right with a speed of 50 miles per hour. The question is, what is the speed of the baseball relative to the car? Well, if the car were just sitting here with the person, the baseball would be traveling 80 miles per hour relative to the car as well. But the car is moving relative to the person. The baseball is heading to the right relative to the person. The car is also heading to the right relative to the person. The baseball relative to the car, it turns out, is traveling with a speed of 30 miles per hour headed to the right. Or if you want to think in terms of a velocity, the velocity of the baseball relative to the car is 30 miles per hour to the right. All right, so the baseball has a different velocity relative to the person and relative to the car, since the person and car are in relative motion. The second postulate of special relativity says that light travels the same for all observers in vacuum. So let's take this example now and translate it to light and see how this says something different than this for light. So instead of having a person throwing a baseball, let's have a tower projecting light to the right. So the light emitted by this tower is heading to the right with speed c. Now let's imagine a UFO flying past the tower to the right with a speed relative to the tower of c over 3, 1/3 the speed of light. The question is, how fast is the light emitted by the tower traveling relative to the UFO? Well, if we use this same logic, remember here we said, oh, to get the speed of the baseball relative to the car, I went 80 minus 50, got 30 miles per hour. Well, if I use that same logic here, light is traveling at c relative to the tower. UFO is traveling at c over 3 relative to the tower. To get the speed of the light relative to the UFO, I take c minus c over 3. I'd get 2c over 3. I'd get that the light is traveling at 2/3 of the speed relative to the UFO as it is relative to the tower. The second postulate of special relativity says that's not correct. The light emitted by the tower travels at speed c relative to the tower and also travels at speed c relative to the UFO, regardless of how fast the UFO is traveling relative to the tower. It seems counterintuitive, but we now have over 100 years of experiment that demonstrate that light travels the same speed relative to all observers. So this addition we did here to take 80 minus 50 and get 30 for the speed of the baseball relative to the car, that works for people, baseballs and cars, but it doesn't work for light. I can't take speed of light being c relative to this tower, subtract off c over 3 for the speed of the UFO and say that the speed of this light is 2c over 3. It doesn't work. The speed of the light emitted by the tower travels at the speed c relative to the tower, and it travels at speed c relative to the UFO, regardless of how fast the UFO is moving relative to the tower. That's just the way it is. Not surprisingly, this counterintuitive postulate, which turns out to be true, gives rise to counterintuitive consequences. We'll explore some of those consequences in subsequent videos, such as length contraction and time dilation. Stay tuned, and thanks for watching.